Let's discuss the property of eigenvalues of Hermitian matrix. The property says that eigenvalues of Hermitian matrix is always real. Let's look at the proof of the property. Assume that lambda is the eigenvalue of the Hermitian matrix A. Then we have the equation Ax equals lambda x, where x is the corresponding eigenvector of the Hermitian matrix A. We know that eigenvector is always non-zero and it's a column vector. Pre-multiplying equation 1 by using x conjugate transpose, we obtain the equation x conjugate transpose Ax equals x conjugate transpose lambda x. Note that x conjugate transpose is a raw matrix. When we take transpose conjugate or conjugate transpose of equation 2, we obtain the equation x conjugate transpose Ax the whole conjugate transpose equals x conjugate transpose lambda x the whole conjugate transpose. We have studied reversal law for inverse of product of matrix, transpose of product of matrix, and adjoint of product of matrix. We studied that AB the whole inverse equals B inverse into A inverse. AB the whole transpose equals B transpose into A transpose. Adjoint of AB equals adjoint of B into adjoint of A. Similar reversal law applies for transpose conjugate operation as well. We have AB the whole conjugate transpose equals B conjugate transpose into A conjugate transpose. And just like we studied A transpose the whole transpose equals A inverse the whole inverse equals A, we have A conjugate transpose the whole conjugate transpose equals A. We make use of these two relations. Here we group the product of matrices as x conjugate transpose into Ax. So we consider Ax as one matrix and x conjugate transpose as other matrix, and we apply conjugate transpose operation. Then we have Ax conjugate transpose into x conjugate transpose the whole conjugate transpose. This becomes x by following this property, and again we apply reversal law here so that we obtain x conjugate transpose into A conjugate transpose. Here again we make use of the same property. We apply the reversal law and we obtain x conjugate transpose into x conjugate transpose the whole conjugate transpose. This becomes x by using this property. Now lambda is a scalar quantity and we don't know if it is real or imaginary. If it is a complex number, it has to be associated with the conjugate sign as well when this operation is applied on lambda. So lambda bar is appearing in all the following steps. We have A conjugate transpose replaced by A because it's given that A is Hermitian matrix. So A conjugate transpose can be replaced by A. Now we have Ax replaced by lambda x because by equation 1 we have Ax equals lambda x. We may take out lambda outside the matrix multiplication because it's only a scalar quantity. Thus we have lambda into x conjugate transpose into x equals lambda conjugate into x conjugate transpose into x. We bring both the terms to one side and equate the other side to 0. Thus we obtain lambda minus lambda bar into x conjugate transpose into x equals 0. Here the possibilities are lambda minus lambda bar equals 0 or x conjugate transpose into x equals 0. But x conjugate transpose into x is never equal to 0 because we have x is the eigenvector of Hermitian matrix A. Therefore x is always non-zero and x is a column matrix. If this is the column matrix x, then we have x conjugate transpose represented in this form, which is a row matrix. And when we multiply x conjugate transpose into x, we obtain an equation of this format, that is x1 conjugate into x1 plus x2 conjugate into x2 plus etc. plus xn conjugate into xn, which can be rewritten as modulus of x1 the whole square plus modulus of x2 the whole square plus etc. modulus of xn the whole square, which is always a real and non-zero value. We could replace every product x1 conjugate into x1 equals x1 square modulus and x2 conjugate into x2 equals modulus of x2 the whole square because we have the relationship z into z bar equals modulus of z the whole square. Thus we may conclude that x conjugate transpose into x is always a real quantity and it's always non-zero. So the only possibility is that lambda minus lambda bar equals 0, from which we obtain lambda equals lambda bar or lambda equals lambda conjugate. If lambda takes the format lambda equals alpha plus I beta, then lambda conjugate is alpha minus I beta, where alpha and beta are real numbers. Since we obtained the condition lambda equals lambda conjugate, we have alpha plus I beta equals alpha minus I beta. From where we obtain 2 times I beta equals 0, or we obtain that beta equals 0. Since beta is 0 in the expression of lambda, we have lambda equals alpha, which is purely real quantity. Hence, we can conclude that lambda, which is the eigenvalue of the Hermitian matrix A, will always be real.